Good afternoon. My name is John Stone. I'm the Senior Research Programmer at University of Illinois, and I'm the lead developer of VMD. VMD is a molecular visualization and analysis tool that's used by researchers all over the world to analyze, prepare structures, and visualize the results of molecular dynamics and various other kinds of molecular simulations. So the goal of these simulations is basically to provide the scientist with what you would think of as a sort of computational microscope, to allow them to be able to see events that are either on a spatial scale or on a time scale that are too fast to be observed in experimental imaging machinery like microscopes, and to allow us to understand the details of how some of these machines work. Basically, the computer helps us answer questions that the experimentalists really don't have any other way to determine. So working with the experimentalists and the computational simulations, we get a picture of lots of details about how these things work. So getting to ray tracing, so VMD has had support for ray tracing for a very, very long time, going back to long before I even worked on the program in the early 90s. When I came to University of Illinois in 1998, one of the early things I did was I interfaced VMD to the ray tracing engine that I developed over several years as a graduate student. And as time progressed, this ray tracing engine became more and more tightly coupled with VMD, and VMD began to exploit things in the ray tracer that I couldn't do with just any renderer that was out there, even commercial renderers that had, very powerful feature sets. And basically, as of over the last couple of years, even though the ray tracer itself, Tachyon, had been a parallel renderer from the outset, VMD wasn't really fully exploiting that. And as we started running VMD on the supercomputers where the simulations are actually done, it became critical that we did the rendering in parallel also. And then most recently, we've adapted VMD to do ray tracing interactively. And this is what you're seeing here in all the demos on the side of the auditorium here. We've now gone from, a time period in 1994 when I first wrote Tachyon, running on a 32-node Intel IPSC860. It would take me 8 or 10 minutes to render an image with 32 processors, and now this is something you can do in about 50 milliseconds. And over a period of time, my ray tracing engine got progressively more performant and sophisticated. And at the point when I started working on VMD, then I really started rearranging that code to be orientated more for molecular visualization. And I'll show you a bunch of example images. And these began with Tachyon, which is the code that I wrote, but you should think of them only as exemplary because you can do these things with OSPRay as well. OSPRay has all these capabilities and many others. So why would we use a ray tracing engine for a molecular visualization tool? Well, there are a lot of reasons. First of all, these scenes are very geometrically complex. There's a lot of high detail structural information in here. The relationships between parts of these molecules are important, their spatial arrangement, and so being able to see these details easily is important. And one of the things we can do easily in a ray tracer is we can have things like fog and shadows and ambient occlusion lighting, as you've heard earlier, path tracing, things like this. These are easy to incorporate in a ray tracer, and the application that defines that scene to the ray tracer really doesn't need to know about the minutia of the shading. And the benefit of having these things in a scientific visualization tool is some of them, for example, ambient occlusion lighting. The beauty of something like ambient occlusion lighting is it's essentially an automated technique. The scientist does not have to become a professional computer graphics lighting engineer. They don't need to place their lights manually. They can just look at a structure, and in almost any reasonable orientation, they get a lot more information than they would if they used a conventional lighting model. And so the last challenge, and this one is a difficulty for ray tracing to some extent, is that these are all time varying structures. And so what that means, if you compare a ray tracer versus something like OpenGL, to get the performance like I was talking about, to be able to do things like interactive ray tracing, we're very dependent on spatial acceleration data structures of various kinds. And this is really sort of the Manhattan Project of ray tracing, is how do you make that really, really, really fast? Because that's ultimately what will limit ray tracing for time-varying data sets. And that's what gives us the performance for these interactive renderings. So the particular needs of molecular visualization, as it turns out, are really, really well suited for ray tracing. So we draw a lot of spheres, a lot of cylinders, obviously a lot of triangles too. And so ray tracers in the 90s, the reason why we would have used them is because we could get higher quality geometric renderings even with simple shading. And then as time progressed and we were able to incorporate more sophisticated lighting, it became those two things. In the modern context, we also get a massive reduction in the memory footprint. This didn't used to be a big consideration. You know, it only takes about 12 bytes per atom per time step to store a molecular structure and its coordinates. And turning that into polygons, even back in the 90s, you know, you're only talking about 10,000 atoms. But now we have people working on structures that have billions of atoms, and this will get bigger with time. Certainly the material science people are already working on structures that are in tens of billions of atoms, and this is now an issue. So you can't be taking every atom and rendering hundreds and hundreds of triangles to make it look like a sphere, and so that's why people are talking about using techniques like imposters. Imposters are essentially an OpenGL trick for rendering a sphere by doing ray tracing in a shader. And so this is exactly what ray tracers are well suited for. And so the other thing we get out of a ray tracing algorithm, that acceleration structure gives us the occlusion culling. You know, if you were to do this in OpenGL, you have to go through a lot of special, deep, complicated OpenGL hacking and occlusion query extensions and things that are optional features of OpenGL to get that kind of performance. But in a ray tracer, this is just part of the fundamental algorithm. The spatial acceleration data structures are what let you do something like Aaron has a nice demo there showing something like 30 billion particles. How can you do that? The reason you can do that is because you're not really drawing all that stuff. You're drawing what is seen and you're avoiding drawing the majority of it. And so this is what makes ray tracing really great for systems like these. Maybe a more contemporary example where rasterization has a very difficult time is on sort of non-planar projections. And this is of interest. For example, we're going to be doing movie renderings for the National Science Foundation that will be put into planetariums all over the US. And planetariums have a hemispherical projection like this. And if you want to render it very high quality without all kinds of distortions and artifacts, it's much easier to do this in a ray tracer than in various rasterization-based schemes. Rasterizers weren't designed for non-planar projections. And doing that in stereo is even harder. And so this is a case where, because in a ray tracer we're doing this projection math on every pixel anyway, it is a trivial thing to then write a primary ray algorithm that will do an arbitrary projection, whether it's a hemispherical projection, a cube map, an equirectangular projection. I think OSPRay already has an implementation of equirectangular projection in there. And that's also interesting because you need these things for projections for VR headsets and a number of other cases. So in the case of lighting, I'll just give you a simple example. You know, if you just write simple OpenGL, you can take a virus capsid, cut it open, and you see something like this. If you look at this image, you can't really see any of the interior structure of that virus at all. If you implement a simple hard shadow algorithm, then you see a little bit of the interior structure, and then if you use something with like ambient occlusion lighting, now it really stands out. Now there are tricks, you know, in the old days, before we had better methods, we could make reasonable images using tricks like depth queuing or fog to help elucidate the back parts of the structure from the front. But the problem is when you have pockets that are very shallow, depth queuing that works for a big depression doesn't work for a small one. And they're sensitive to the orientation of the structure and the view. So these are all things that a scientist doesn't want to worry about. They just want to be able to see the structure clearly as if they were holding it in their hand. And similarly, you know, we can also have you know, the same sort of sophisticated shaders you would write in GLSL or something like that. And the goal of using all this advanced lighting for a very minor increase in the computer time to render an image like this, the impact on the, you know, the image that results from that for the viewer is that they can immediately interpret which things are in front, which things are in back. A clouded, heavily occluded object like this, where there's a lot of geometry stacked over the top of itself, if you don't have some kind of ambient occlusion lighting or shadows, it just looks like a plate of spaghetti with terrible lighting, and you can't tell what the relationship between the different pieces are. One of the challenges then, as we go forward, is the size of the simulations people are able to do, and maybe not even the simulated structure, but if you have things like periodic boundary conditions, or you have instancing, these are things that are well handled by ray tracers historically, going all the way back to the 80s. People were able to do instancing very efficiently with ray tracers. And so this is one such example, and really in the molecular dynamics simulation, you're only going to simulate one of these pairs of rings around this, and the rest are all periodic images. But when you want to make a visualization of that, if you were to do it in OpenGL, you have to draw this n times. If you're doing it in a ray tracer, you can define the primitive and then make instances of it, and it doesn't take up any more memory. So that's a nice example. So the challenge with ray tracers has always been related to performance. They're doing a lot of difficult floating point arithmetic. There's a lot of memory accesses. Making that fast is very hard. So although I spent a lot of time in my youth writing Tachyon, this was in an era when we really didn't have machines with vector acceleration extensions. And the compilers of that era certainly didn't exploit any of those things either. And even now, today, if you use the latest compiler technologies, the languages we have and the primitives they offer are not really able to give us what we want performance-wise. And so that means even a well-written ray tracing engine, if you have not gone to great lengths to make it vectorized, the compiler isn't going to do it for you. And so this is, in fact, why we need things like OSPRay and SPIMD languages like ISPC. So the answer to this question is we can use sort of, what would I say, a compiler and a language technology that is designed to basically solve this problem above everything else. That's what it's for. It's for solving this problem. And until we had compilers like this, you would have had to have written these things in assembly language, and people did. Ingo certainly did more than his fair share of assembly language ray tracing, and many other people going back quite a while. And so then that combined with high-level ray tracing frameworks basically now gives you the opportunity to use these rendering kernels at a much higher level. So you yourself don't even have to write the low-level mechanisms that do all this. So Intel has OSPRay, which you know, I was very keen on when it first came out until I discovered it was only capable of rendering triangles. And I thought, all right, well, talk to me again when you can do something besides triangles. And so then Intel now has OSPRay. And for me, this was what I was waiting for. Until I could have all of the other geometric types, the net win from the advanced vectorization would have been canceled out by the loss in efficiency for having to convert a sphere into 1,000 triangles. And so now that we have OSPRay, we have all of the types of geometry that we need for a tool like VMD. And the benefit for somebody like me is, even though I have a ray tracer already and it runs reasonably well, I am not prepared to go and spend the time required to do the detailed performance tuning for Tachyon to make it fully exploit a platform like Knight's Landing. And so this is basically what Intel is doing with OSPRay. And so even though I have a perfectly good ray tracer that already implements every feature VMD would ever need, it is not going to be performant enough on a platform like Knight's Landing. And so this is where OSPRay is a huge help. And what's interesting, up to this point, I have been using the features that are just completely standard part of OSPRay now. There is nothing uniquely suited to VMD in any of the things you're going to see in my talk. I'm just using the same code that everybody else has at the present time. But what'll be interesting then is at some point when I have, sort of done everything I can with the mainstream OSPRay, you can write your own renderer and you can customize it and you can add your own primitives and do things that the mainstream code maybe doesn't do yet by adding a new renderer implementation. And so when I've gone as far as I can with the standard implementation, that's probably what I'll do later. And so the way that OSPRay is integrated into VMD, VMD has a big molecular data structure internally, and there are a bunch of calculations that basically transform that into graphical representations, and they become a display list. And then later in the program, this then fans out to a huge number of potential renders, depending on if it's a windowed OpenGL display, a cave, or something like that, a VR display, and in this case, Tachyon or OSPRay. And so what's great is it took me, I don't know, I think a matter of a few days to get the first OSPRay code to work with VMD. And since then, mostly what I've been doing has been replacing my prototype implementations, which were quick for me to write, with better implementations that do a better job of exploiting the natural memory layout that OSPRay prefers and using newly added features in the latest versions of OSPRay so that I save memory, I have fewer objects in the scene, and it's a more direct conversion of what VMD stores internally to what OSPRay ultimately renders. So to give you an example of some deficiencies though, so at the moment I flatten the entire scene graph into I-coordinates and then give them to OSPRay, and this gives me great performance and it's wonderful for the interactive rendering we do now. But if I want to go back now and do molecular dynamics trajectory playback where the atomic structure is changing every time step, this is basically, I would describe it as overhead. This needs to not happen. I need to basically use the original molecular coordinate system in the scene that I give OSPRay, so this will require some extra machinery on my part that isn't there yet. But when I do that, then what'll be really nice is OSPRay and the internal data structures in VMD will be almost the same, so at some point I will get to the point that there will no longer really be a copy anymore. Or if there is a copy, it'll be because there's a loose end somewhere in some API where we need to make it possible to do it with zero copy. But the idea would be then the only thing that would really have to happen is your spatial acceleration data structure would have to get updated as the scene changes. But other than that, for the better part of it, my goal is to basically eliminate copies or reformatting or pre-transformation of the geometry before I give it to OSPRay and just give the raw arrays to OSPRay along with some transformation matrices. So the structure of the batch processing loop, I mean, what's nice about OSPRay provides a very high level abstraction for the frame buffer. So it's basically, you define your scene in terms of some material properties, the geometry that you're going to draw, whether that's a bunch of triangles or spheres or what have you. And once you've defined all those things in your lights, then you can just define what kind of frame buffer you want. Do you just want a color buffer, or are you planning to do something with ambient occlusion lighting that requires a large sample count, something like this, or you want to iterate over and give a status update to the user? You can use an accumulation buffer, and then you basically just have something like this where you call the OSP render frame. It renders to this accumulation buffer, and you can just do that as many times as you need to accumulate the number of samples you're after or to achieve some convergence criteria, whatever it is that you're shooting for. And when you're finished, you can call OSP map frame buffer, write the image to disk, do whatever it is that you were going to do with it, send it over the network, and so on. To convert that from a batch process to an interactive renderer like the ones you're seeing here or the VMD demos that will be shown later in the week, it's basically the same overall structure, except that instead of looping just in tight loop here, we have a few extra steps. We're rendering the frame, checking for GUI events, things like this. We map the frame buffer, then we draw it with OpenGL to a screen somewhere, unmap it, and then continue. And so it's a little bit less tight loop, and we're changing state possibly or restarting and clearing the rendering, but it's also very easy to write. This is actually much easier to write the API is very simple, it takes 5 minutes. So even if you have never even thought about how this works, this is something that I think a beginner can learn how to do in a matter of an hour of fooling around. In fact, there is some sort of, I think it's called OSP tutorial.cpp that is in the OSPRay distribution that implies this. I don't know if it shows ambient occlusion lighting, but I remember it has a comment in it somewhere that says, oh, this is how you do an arbitrary number of samples. So this is very easy to use. And now I'll just show you a few of the early renderings I've made with OSPRay in the current version of VMD. So this is a little DNA strand going into a silicon nanopore. I forget what the atom count is. It's probably a few million. And this is just showing you your typical ambient occlusion lighting and hard shadows, and it's a very big structure. And and this plays at, I think on my desktop workstation at work, it's in the 20s of frames per second. And I think they have this running somewhere. This is a polio virus. So the first one, excuse me, the first scene I showed, this one has a variety of geometry. You're seeing spheres, cylinders, and triangles, triangle meshes, and a large number of geometric primitives. This one is primarily just triangle meshes that were computed from a Gaussian molecular surface with simple material properties. This is a ribosome. So this is a antibacterial drug target. And you can see it also has nucleic acids that are drawn with nucleotide cylinders, triangle meshes, and triangle strips. There's a lot of opportunity for me to optimize the memory footprint for some of these geometric structures right now. I think at the moment I'm flattening a lot of these triangle meshes, but it's not because OSPRay can't use those. It's just that I haven't had the time to write the code because I've just been doing this over the last few weeks in what little time I had. And this is another example that's a large photosynthetic membrane patch, and this is also a large number of triangles. So this is about, the simulation for this is about 20 million atoms. The disk we're seeing, I think, is about 3 million atoms, give or take, and there's some transparent surfaces in there as well. And so one of the main targets for me in using OSPRay, as I said, is to basically be able to do ray tracing at high performance on the upcoming Knights Landing hardware. And so the prime example of which will be the machines at Argonne and NERSC, the Cori machine at NERSC and Aurora at Argonne. And so this is where I'm really excited to see the benefits of OSPRay as compared to my own Tachyon code and various others. So that's the end of my talk. So if you have any questions, please ask.